any questions before we start? Okay, so I remind you that we've been talking about 2D and 3D images in this course. Almost all my examples in the class have been in 2D, partially because what I have on the essay writing area is 2D, and it's easier to show that. And I've also given lots of examples in 1D. But please be informed that the exam will certainly have questions about the extensions to 3D. Okay? And of course, in general, there can be even more dimensions, such as time. But the exam will not go into spatial dimensions beyond 3. Okay? Of course, for computer representation, for computer storage, we understand the image to be sampled in position at what I call pixels in 2D or voxels in 3D. And for the discussion I've had in lecture, the sampling distances in each dimension have been the same, right? And so we've been using integers as the location, the pixel locations, 1, 2, 3, 4, 5, up to whatever it is. In your homework, it's been 128 in each of X and Y, but it can be. And they need not be square. That is to say, you could have more pixels in one dimension than the other, but the exam won't test that variation. It's also possible for the distances, the delta x's in one dimension, the distance between pixels could be different than in 2 dimensions. For quite a number of medical images, that in fact is the case, right? The methods essentially can be understood to make 3D images by a pile of 2D slices. A 2D slice at one depth and another 2D slice at the next depth, and so on, piled up on top of each other. And the spacing between, and while each slice typically has the same distance between pixels in the two-dimensional direction, 2 directions within slice, the between slice directions are often greater than the between slice directions in the other. The between slice directions distances are greater than the between pixel directions in the slices. That's true. That's something that one has to take care of in those special situations. But the exam won't cover that extension either. Okay? I have mostly used pictures that you would take with your camera as examples, but of course this course is a biomedical engineering course as well as a computer science course, and there are lots of medical image sources to which these same ideas apply, and my own personal research has largely been focused on images from radiographs, from X-rays, from CT, from MRI, from ultrasound. The ideas that I'm talking about apply to them as well, except that in those imaging modalities that require a reconstruction, that is to say, are made from, like CT, where you have images taken essentially in a variety of directions, and then and those 2D images are combined into a 3D image, or if you're doing it within a slice, 1D images are combined, reconstructed into 2D. That reconstruction process is itself a processing step, involves convolutions. It involves shift invariant linear operators. And then thereby the noise properties that I've talked about for images that are directly sensed rather than produced by reconstruction are different because there's essentially this extra convolution that's been applied in the reconstruction. Therefore, the exam will cover only noise situations where we have this uncorrelated zero mean noise. Okay, so in other words, that it is at every pixel there is independent noise values that are independent of what's in the other pixels. Okay. Okay. Any questions that have come from this slide? Okay. So we have the idea then that images are usefully described as a linear combination of basis images. So we have this idea I'll say the number of image elements, the number of pixels or the number of voxels. And the idea that if we have some number, capital M, of image elements, we have that same number of basis images, and that we're going to think of an image as a linear combination of those basis images. The first really the first straightforward set of basis images that we talked about were the delta images, which sometimes I wrote as delta and sometimes I wrote as E, okay. And those are the images that have one image element and zero in all the other image elements. And when that's the case, the AKs are the intensity values in that element, right? But the locality of those images is far too small for this to be a fully useful representation. And we frequently actually want basis images that are either global or, better still, we have found rather local, but not at the smallest level of detail. Essentially, the E images are the smallest level of detail we could conceivably use. Okay? And then we said because we're familiar with images being expanded about a point, and in terms of derivatives, we learned about the Taylor basis, which has basis images which are, let's see, 1 everywhere, x minus x0, y minus y0 in 3D, z minus z0, okay, and then, well, strictly, yeah, and then x minus x0, squared over 2 factorial. Strictly, these are over 1 factorial, but 1 factorial is, of course, 1. And x minus x0, y minus y0 over 2 factorial, and y minus y0 squared over 2 factorial, and so on. And these are expanded about a reference point, x0, and are local to that, in the sense that the approximation that's developed is adequately accurate near x0, x0, y0. Notice that in 3D we're talking, we will also have, oops, what do I have? You know, if it's in three dimensions, I'm going to also have, let's z minus z0 over 2 factorial, and y minus y0, z minus z0 over 2 factorial, and z minus z0 squared over 2 factorial, and then higher order terms, the cubic terms, and so on. And the idea that is that those basis polynomials get evaluated at every pixel position x, y, z, or in 2D x, y, right? And thus form an image. Okay, these polynomial expressions turn into images by evaluating them at the pixel or voxel positions. And this produced a typically 2 local approximation still, but it forced us, because the coefficients, instead of being here pixel values, the coefficients are appropriate directional derivatives, mixed partial derivatives, right? So the coefficients of these polynomials are first derivatives here, and second derivatives here, and going on third derivatives. And then we understood that derivatives of images at any given point can be understood as appropriate partial derivatives in x, y, and z, which are directly associated with here. So you have the pure x polynomial. The coefficient in question is di by dx. And the coefficient here is di by dy, and di by dz here. And for this one, it's two x terms, so it's the second derivative twice in x. And this one has d2 I by dx by dy, which maps to, and so on down the line, right? And we understood these tuples in terms of tensors, right? And the common confusion is the order of the tensor, which is the order of the derivative, and the dimension of the space. We've been talking about spatial dimensions of 1, 2, or 3, and orders of derivatives of 1, 2, 3, 4, whatever. Okay, order has to do with the, if you're talking about order 4, you have, you're talking about fourth derivatives, and that corresponds to a fourth tensor. And these tensors are generalizations of the simplest zero tensor, which is just a one-by-one thing with a value at that one position as a scalar. A one tensor, because there was a zero, that was a zero tensor. The one tensor is a n-by-1 matrix. For the derivatives, it's the gradient. And it just lists all the first derivatives in the cardinal directions, where n is the dimension of the space. For the 2 tensor, it's something we call the Hessian. It's the D2, big D2I tensor, and it's n by n, linear thing, applied linearly. It's a matrix, right? And then for the third derivative, it's an n by n by n linear thing, some kind of an array that's in the form of a box. Okay? And so on. So we understood that there were tensors, and that these tensors allowed us to evaluate derivatives in any direction, or direction tuple, which you need for a k derivative, you need a direction tuple of k respective unit direction vectors that I called u1, u2 up to uk. Okay? Okay, so you need to understand these tensors, and you need to not be confused between image dimension and order of derivative, order of the tensor. Okay? Questions on any of that?
For the Hessian in the gradient case, is it only a 3 by 3 with the diagonals being x dx squared dy plus ab squared?
That's right. Yep. Right. Exactly. So here we are, d2 I by dy squared here, and d2 I by dx by dz here, and d2I by dy by dz here, and d2I by dz squared. And when we write the 2 tensor, which is the 3 by 3 matrix, the xx, okay, so you can think of it xyz that way and xyz that way. And so d2, so this is xx, so it's d2I by dx squared, and the diagonal y, d2I by dx squared. And down here, d2I by dx squared. And over here, let's see, it's xy, so d2I by dx y, and so on. But realizing that the property of derivatives is that the order of the derivative, and the order in which the second derivative is taken as one, a derivative of x followed by a derivative of y, or a derivative of y followed by a derivative of x does not matter. We have that this is strictly d2I by dy by dx, but because it's the same as this guy, we can write that these two are the same. And so what ends up is that this matrix turns out to be symmetric, right? Because whether you do x and then y or y then x, it doesn't matter. So that the tensor, the derivative tensor, is represented as a symmetric matrix. right? And it's 3 by 3 in for 3D images and 2 by 2 for 2D images. Other questions? Please realize that although I've written this guy as one basis image, it's really two of them with the same formula. There's the x minus x0, y minus y0 polynomial, basis polynomial, and there's the y minus y0, x minus x0 polynomial. So although there's only one instance of this, there's two instances of this, one instance of that, and so on, because of the fact that you have both of these terms in the Taylor series. Yeah.
I would forget, does that mean for that particular divided by 2?
Well, it depends on how you think about it. If you write it as two of them, then each of them is divided by 2. If you do the algebraic simplification where you sum the 2 and only apply it once, then it's multiple. The 2 is canceled by, and the denominator is canceled by 2 in the numerator.
I think you were summing I didn't realize.
No more questions? Let's go on. We then started to talk about that instead of having just an image, we were going to have operators on images. And we've used lots of different operators on images. The first one might be an operator that turns an image into its first derivative, into its gradient, for example. Let's say into its di by dx's, into its di by dy's. Another operator that we talked about was operators for lowering the noise level, typically by convolution with a Gaussian, for example. We talked about ones that sharpen the object, which basically involve applying an operator that inverts the blurring that happened previously, before you produce the image, either by the camera or by the camera and any further computational calculations that you've already done. But the general idea was that we produce a new image, which is an operator on the input image. And then we were interested in operators, especially that had particular properties. The so-called invariance, or mathematicians say equivariance properties. Okay, and the invariances that we're especially concerned with are invariances to geometric transformations of translation, rotation, and spatial scaling. And so we needed a definition of invariance of an operator T to an operator G, which, and the definition was it didn't matter in which order we applied the operators, the geometric transformation, or the operator we're looking for variance. And we also saw that meant that T is the same as G, G, T, G. Okay. Okay, then we we're particularly interested in operators that were linear. We've been talking almost entirely about operators that are linear, but you should think about what some examples of operators that aren't linear, so you make sure you understand what linearity means. But linearity means that of P of I1 plus I2 is P of I1 plus P of I2 for any pair of images I1 and I2, and P of alpha I1 equals alpha P of I1 for all input images. And that's linearity. And so we were interested especially in the operators that were both linear and translation invariant. And translation invariant is just another word for shift invariant, right? And then the next thing we said was, computationally speaking, it was going to be very much advantageous if these psi k's produced were uncoupled. Okay, that is to say, when you applied T space, when you applied T to one of the basis images, you got simply a multiplier times the basis image. And those multipliers and images that have that property are called the eigenimages or eigenvectors of T. And these guys, sometimes written as lambda k, are the k of the eigenvalues of T. And so that we say when you apply this to psi k, the resulting image jk has no terms, has zero coefficients in all of the rest of the basis images other than k, and that this made life particularly easy. And then we saw the interesting property that for the shift invariant linear operators, they shared the same eigenimages, the sinusoids. Each operator had its own eigenvalues, its own coefficients, but it had they all shared the eigenimages. We also saw that these operators could be expressed as a very high order matrix multiplication with a symmetric matrix. And because of the symmetry, the eigenimages were orthogonal. And that orthogonality was really helpful because you can compute the coefficients of any image in that basis simply by dot producting the image against the eigenimage, against the basis image. And so this eigenbasis turned out to be a really useful thing. Questions on anything so far? Okay. as I said, for that large class of operators that were shift invariant linear operators, we spent a lot of time on understanding what they were. First of all, that the sinusoids were the I probably should not to confuse you. Let me call those DKs rather than AKs, just because I use the AKs as these guys, the coefficients. Okay, we saw that the sinusoids had a lot of nice properties. They were invariant. They produced representations that were invariant to rotation and translation. Well, by definition, since we're shift invariant, they should be shift invariant, but they're also rotation invariant. And they're separable in the image direction, so you can understand things as sinusoids in the x direction multiplied by sinusoids in the y direction multiplied by sinusoids in the z direction in 3D. Right? And we saw 3 different ways of understanding the coefficients here, these AKs, when the psi k's were the sinusoids. Okay? And sinusoids have frequencies, and the frequencies were an integer over the size of the number of pixels in that particular dimension. So if you have a 512 by 512 image, n is 512 for the rows and 512 for the columns. And by the way, if you happen to have a 256 by 512 image, then for the x direction, n is 256, and in the y direction is 512. That's all. Right? But anyway, that these things were, if the integer, let's call it j, then we're talking about a frequency for that sinusoid. That's nu j over n. And the basis images are then according to the various values of j. But be careful, because j can be negative 0, all positive, integer. So you get positive frequencies and negative frequencies. Anyway, the idea is that these coefficients then come as duples for a particular frequency. And the duples can be understood as the main one we talked about as a magnitude and a phase. Okay, but alternatively, those can be turned into how much you have a cosine at that frequency and a sine at the same frequency, and how much there is of each of the sine and the cosine respectively. And that can be turned into a complex number. Again, a real part and an imaginary part. But either way, they come as duples. So that you have a slight modification of the situation here, where in this expansion we acted as if the ace of k's are singles, are scalars. But now, because we think frequency by frequency, they're really duples. Right? Questions? And then we have this algorithm for turning an image into its coefficients. And for the sinusoids, that's called the discrete Fourier transform, DFT. And then we have a very special, computationally very useful form of that DFT algorithm, which uses divide and conquer ideas and is called the FFT, the fast Fourier transform. But it's just DFT. It's just a very special algorithm for computing a DFT. It computes these coefficients. And its inverse is so similar to itself that the same algorithm works in reverse with one little sign change in the throughout the algorithm. And thus, the DFT algorithm turns intensities as a pixel into coefficients, and likewise it turns the alternative form, given the number of coefficients, produces the image intensity. I have warned you, you have seen that there's all sorts of complications in regard to exactly where which frequency occurs. And I'm not going to, on the exam, make, focus on those confusions. But I am going to focus on the periodicity, the so-called wraparound problem, where when you work in the frequency domain, you understand that you're acting as if the image were periodically repeated. And likewise, when you're working in the space domain and you want to think about something that was originally understood in the, sorry, let me say that in different ways. If you have space and you have frequency, either way, you have to understand that the input needs to be thought of as periodically repeated. Okay, so you have this set of frequencies, but also other frequencies next to it, more negative or more positive in frequency. Over here, and likewise you have periodic repetition in space. And so if you work directly in the space domain, then you can avoid this periodic repetition problem, which essentially means that the bottom of the image is next to the top and the right side is next to the left side. And the same thing in the frequency domain, where we're talking about essentially positive and negative frequencies in both x and y. And the positive frequencies are next to the negative ones in the y direction and likewise in the x direction. And that periodicity is an important thing and could be part of the exam. We saw, okay, any questions so far about the shift invariant linear operators and the sinusoids as the basis image? Okay, then we saw that multiplication of these coefficients for each k were done by multiplication of the a k's by the b k's. We expand the image in terms of its basis images, and then we multiply. The coefficients of the basis, sinusoidal basis images by their corresponding eigenvalues of the operator that we're applying. But that can be shown to correspond to convolution of the image with a convolution kernel, and that the convolution can be understood as having an operator at every point in the image that essentially makes a linear that replaces each point in the image by this kernel, and then we add up over all the individual pixels. These effects of replacing the image intensity by the image intensity times the kernel centered at that pixel. And then we saw that that was the same as thinking about output by output, that each output result at each pixel of voxel in 3D. The result was a linear combination of all the surrounding voxels. And that linear combination just turned out to be the reflection of the kernel, about 0. So this two-way looking at things, output by output, where the kernel h of minus x is what you need when you look at it output by output. Or h of x, which is what each pixel is whether when you think of it as input by input. There's an important thing for you to know and could be examined. Yeah.
By output by output.
What?
What exactly do you mean by the output by output?
Well, for each output pixel, what input pixels, how do input pixels contribute to it? That's what output by output is. You think of act separately for each output place. Okay, so you have an image, and you're asking what the result is T. So this is at a particular result picture. That's output by output. Input by input says I have a particular input pixel, and how does it affect the output? That's clear? And the answer is whatever the intensity is here, it gets multiplied by h of x minus, if this place is x0, it gets replaced by h of x minus x0 times I0, that value at x0. But when you do it output by output, and you're at some, I'll call it x1, then what you have is that output at x1 is h of minus x minus x0 times I sub x summed over all the x. Yes, thank you. Excellent. Okay. We saw that convolution, and thus its calculations by the frequency domain are commutative and associative, so it doesn't matter in which order you apply shift invariant linear operators in cascade. And it doesn't matter in what order you combine them, right? If you're going to apply operators T1, T2, and T3, where you apply first T1 and then T2 and then T3, you can compute T1 and T2 result and then apply T3, or you can apply T3 and then apply T1 T2, and because of commutativity and associativity, you can mix and match. And because these decays, because say this right, because these H's, these convolution kernels, are images themselves, you can take them into the frequency domain, the H's, and you get what we call transfer functions or filters, right? And the result is that we can convolve, if we want to apply them in cascade, we can understand as convolving the kernels, typically via multiplication in the frequency domain, and then apply the resulting convolved kernels to the image. So we don't have to apply one of them to the image. We can apply to the image only after we do the cascading. Questions? We saw that match filtering was an interesting way to detect particular patterns in the image. The idea being, if you want to optimally get a response to a particular pattern in the image, you use that pattern as a convolution kernel. And on that basis, we understood that, for example, edge strength, could be understood as convolution with an edge pattern, which is not precisely the same as an edge, but at least in the range of near the edge, was nicely understood as the derivative of a Gaussian. So that you understand the derivative of a Gaussian as a kind of roughly matched filter. And likewise for a barness, we saw that the second derivative of the Gaussian was roughly a matched filter. We immediately, all along in the beginning of the course, we were talking about taking derivatives via Gaussian apertures, but we didn't really get that solid until we came to the second major topic of the course, which was locality and scale, and where we saw that the Gaussian was the best aperture to use. And the result is that, from what I just said, that applying a derivative operator with an aperture. The aperture application is itself shift invariant linear. The derivative is shift invariant linear. You can group the derivative and the derivative operator and the aperture operator, the Gaussian, together, and therefore you get derivative of Gaussian operators at a particular aperture, at a particular sigma. And then we made this notion of sigma in a Gaussian general by understanding the RMS width of any kernel as the integral of x squared, I'll call it h centered of x over all of the image. And h centered means that its average is 0. The average of h of x, dx centered is 0, meaning it's h shifted to its mean, shifted relative to its mean, its average. Okay? And so we have this idea RMS width. Someone should have taught me. I left out the R part. There's the R part. R stands for root, square root. Without the half, this is the MS, the mean squared for Gaussian, it's sigma squared. And so we start to feel comfortable saying sigma is RMS width. And we can use that term in general, but and specifically for Gaussian. And we're particularly interested because we're talking about images, and images are produced by some operator on a scene, and those can be frequently, most often understood as shift invariant linear operators. They have their own h's that they apply, which we call a point spread function, and we can talk about that point spread function's RMS width as a parameter sigma of the image formation process, which is, and we saw that that one will then be cascaded with any computational image computation operator. And so we get the convolution of the camera one and the point spread function, that is the camera one, and the computational H as the overall effect in our final image. And then we saw that when both of these had an RMS width, your point spread function had sigma PSF, and your computational operator had the sigma computational for its kernel, that the overall effect is combined by sigma PSF squared plus sigma computational squared to the half for Gaussian. And approximately so for things that are Gaussian-ish in the sense of unimodal things that fall in both directions from the mode and are symmetric. So that was an important relation. Any questions on anything here on this slide? I've already talked about derivatives via the Fourier basis function. That in the frequency domain, the Fourier transform of those operators, not counting for the Gaussian aperture, were simple quadratics of, polynomials of frequencies. You know, it's nu for first derivative and nu squared for the second one and nu cubed for the third derivative, and so on. Plus constant factors, and worry about the fact that there's the power of the imaginary constant I, which corresponds to a phase shift, if you will, when you multiply by I, or a phase shift of pi over 2, or -1, multiplying the magnitudes by -1. When you're taking second derivative, or I cubed, which is again a phase shift by the opposite pi over 2. If it was plus pi over 2 in the first case, it was minus pi over 2. And then I to the fourth is just 1, and so on and so forth. Okay, but the point is that understanding that the derivatives were these very simple functions in the frequency domain was important to us. And then when we talked about operators, which in the frequency domain, so now we have the Fourier transform of the kernel, that is to say the transfer function. And if we had operators that, I'll call it the magnitude multiplier, that got large either in the frequency, got large as frequency increased in magnitude. That's the one for the second derivative. The cubic one looks like that, and so on. Just nu cubed. That you started to get serious problems if you were multiplying amplifying these components at high frequencies by something where the signal to noise ratio was bad. And so these operators, typically in application, needed to be rolled off after a while. To not have this bad amplification effect because of the noise. It's that bad signal to noise ratio at high frequency. We understood that computationally it was particularly effective for these operators to be separable, which meant you could apply one of the cardinal directions and then on the result another of the cardinal directions, and in 3D then the third cardinal direction. And we were also interested in what the cardinal directions were, if you will, mattered. And that is to say whether tilting the objects in the images should make a difference. And the answer was that we would, if we want not to have bias in that direction, we want our operators in the frequency domain or in the space domain to be isotropic. And it turns out that isotropy in space. That is to say that the image that this H function understood in the value here and here and here and here, and in fact everywhere, all the way around at that distance from the middle, from the 0 position, was the same. And that was true no matter what distance from the 0 position. So we had this rotational symmetry, which corresponds to isotropy of an operator. And that ended up being in the frequency domain and the 0 frequency, the same story. Turned out it was also rotationally symmetric. And we saw in general that distances in X and distances in nu were reciprocally related, right? So big distances in X correspond to little distances in frequency, and vice versa. So a wide Gaussian in space turned into a narrow Gaussian in frequency, as an example. We spent a good deal of time focusing on what happened when we understood an image as being a scene involved with a point spread function, and then we added random noise. And when that random noise was white, that is to say, was uncorrelated, you had this property that in the frequency domain, the Fourier transform of the noise squared the expected square of the half was what we call the noise level, was the same at every frequency. And that sameness is why it's called white. The uncorrelated noise, 0 mean, uncorrelated across space, yields this property. But on the other hand, the image is the scene involved with a PSF, and the PSF looks something like Gaussian. And the result is that the image information gets really small as you get to higher frequencies. And the signal to noise gets bad at high frequencies, and that's why you need the roll-off that we talked about. Exactly where it's all up depends on the resolution of the image, which is to say something proportional to signal of the camera or of the image formation process. Okay, we then went on to talk about pixelization. When you had a continuous image and you wanted to know how to represent it in terms of pixels, it was important to realize that basically what's going on is averaging over every pixel in the scene, pixel region, if you will, the area represented at its center by the pixel value, but averaged over the pixel area or volume in 3D. You had that averaging, and you had this co-multiplication, which was the explicit pixelization. And that we then analyzed that as what happens in the frequency domain, and we saw that an aliasing effect happened, which was pollution of multiple copies in the frequency domain, multiple offset copies of this operation. And that if we were willing to say that the major pollution came from what happened in the just next copy on either left and right, positive frequency and negative frequency, we got at the so-called Nyquist frequency, or folding frequency, we could come up with a explicit formula for how the spacing of the pixels should be related to the RMS width of the image formation operation. Right, and this is a funny formula with five and the particular chosen allowable level. Any questions about that? We haven't spent a lot of time on the sinusoidal analysis because so many of the operators who are interested are shift invariant and linear. We said, but after all, what is particularly good about this Fourier analysis? And ultimately, it means that computing these operations becomes very fast. And the major weakness is that if we're interested in what we're most frequently interested in images, namely where particular objects are and being able to recognize them, that the non-locality of the Fourier, the fact that every single one of its coefficients here depends on every single pixel in the image. And so it can't represent the local properties that you need if you're going to actually talk about an object, where the object is and how it responds to the place that the object is. And so that's a serious weakness. And therefore, we moved on to these scaled, we moved on to these operators that had locality and spatial scale that weren't global. But before we did that, we talked about a new set of basis images, psi k, which were optimal for measuring the optimal in the sense that you needed not this many basis images and this many AKs, but very, very much fewer AKs. And if you took the sum of squared, average sum of squared differences between the training images and their representations, you got a new set of basis images, which were eigen images of A transpose A, where A was the data, the training data matrix after subtracting its mean over the collection of training images. But during that time, we learned some very important pieces of mathematics, and those pieces of mathematics are, at least the results of them, are very important and thus certainly can be examined upon. And one of them is Parseval's theorem, that no matter what set of orthonormal basis images you use, the sum of the squares of the coefficients AK is the same. Okay, and so it's kind of budget. And then this eigenanalysis of A transpose A is what you need to get for your best spending plan. You spend as much as possible on the first eigenimage, on the first basis image, and that results in needing to be the first eigenimage, the one with the biggest eigenvalue. And that we found a much computationally improved algorithm for computing these guys by operating on AAT when the number of training images was way smaller than the number of pixels or voxels in the image. The other major thing that you need to know, take home, understand, is that understanding images in rotated coordinate systems is beneficial, and that any matrix, for example, A transpose A or A transpose, or any matrix, square or rectangular in any direction, involves two rotation matrices and orthogonal scalings in orthogonal directions. And that idea that the eigenimage directions are simply a rotation of the cardinal directions in the space, very high dimensional, but you get a rotation, and those are the directions where the multiplications take place, the gammas. Strictly, what happens is you rotate into cardinal from, and then you multiply everything by, in that way, by the gammas, and then you rotate back, or rotate again. And especially that in the case where A is a symmetric matrix, that these two rotations are inverses of each other. And that's important stuff. Okay, let me see. I got one more slide. Let me pass my hand quickly over it, and then I'll say a few words about it again on next Tuesday. We got into this spatial scale business, and we saw that they were going to be very useful for applying operators in particular parts of the image of a particular scales, and we thought those two aspects of scale that we end up wanting to be proportional to each other, but which are separate. We understood that this picture that I drew somewhere, here, worked for not only the scale, which is where this is 1 over spatial scale, which is to say LOD, the level of detail version. And that thing is going to apply whether we're talking about a sinusoidal decomposition or any other of these orthogonal function decompositions. And we talked a little bit about the multiscale approximation and why the Gaussian was so important. And I'll talk about that next time in review. So I'll let you go now. I hope you all have a relaxing spring break. But please remember that you have to study if you're going to succeed on this exam. You will not, even though you have days to work on it, just figuring out that you have to look things up is not good enough. If you don't know where to look it up.